Many of today's biotechnology companies rely on fermentation to produce their products. In the typical process, a particular microorganism is used to produce a valuable compound or product. Fermentation permits us to scale up that production. Instead of a single cell producing our molecule of interest, we use hundreds, thousands, and then millions and millions of these tiny microfactories to produce many different products on a commercial scale. In fermentation, there are two ways in which the product of interest is produced by the cells. Extracellular production is when the cell secretes the product of interest. Examples of this could be certain amino acids, enzymes, or monoclonal antibodies. In the case of extracellular production, the biomass or cells are discarded at the beginning of separation, and the medium is kept for further processing. Intracellular production is when the product of interest is produced by the cells and kept inside the cell. And during the early stages of separation, the biomass is collected and then disrupted so that the product is released. In our treatment of fermentation, we concentrate on intracellular fermentation. But fermentation is only the beginning of this journey. Let's look downstream at the next process step in the production flow: recovery. The final product of fermentation is called broth. Broth contains the molecule of interest. However, the molecule is still locked inside a host cell. And millions of these host cells are suspended in a pool of depleted media and metabolic waste products. In the next step, recovery, we perform two important functions: separating the cells, solids, from the broth liquid, and separating the molecules of interest from their host cells. Exactly where within the production flow those technologies are employed varies significantly from product to product. Recovery processes commonly use a variety of tools such as centrifuges, cell disruptors, and microfiltration to isolate the product. In this program, we are going to look at a typical recovery process used in the manufacture of GFP, green fluorescent protein. GFP is broadly used as a biological marker, which, if attached to a drug, could provide researchers with a visual story of where the drug goes. It's a fluorescent dye that's very well tolerated by most cells and doesn't interfere with normal cellular function. So how does recovery work, and how does it fit into the total production flow? Here's a very basic overview. After fermentation is complete, the broth is harvested and sent to recovery. Here, the E. coli host cells are separated from the liquid broth, then suspended in a new solution to wash the cells, separated again, resuspended in a new solution, homogenized to break open the cells. The cell debris is removed. Once recovery is complete, the product is sent to purification to be refined and concentrated. But to really understand recovery, we'll need to closely examine our process so we can appreciate what each step accomplishes and why it's important to the process. Let's start with the tools we'll use in the green fluorescent protein recovery process. Those would include a disc stack centrifuge to separate solids from liquids, a homogenizer to break open the E. coli cells, and a 0.22 micron filter to separate any remaining solids in the product solution. Our materials include the broth from our fermentation process, high-purity water that has been reverse osmosis filtered, deionized, and UV sterilized, and a buffering solution to help stabilize the pH of our product and keep it in suspension and prevent the product from degrading. The recovery process is managed through the use of a batch process record. The batch record leads the operator through the process, step by step, with each step requiring a sign-off and separate verification by a second operator. This record also includes spaces for documenting times, activities, operation steps, and instrument readings. Before the process can begin, the recovery area must be cleaned and organized. Any unnecessary equipment or materials should be removed, and the area must be cleaned and disinfected to decrease the level of microorganisms. All equipment must be cleaned, sanitized, and set up as required by standard operating procedures. All required materials and documentation must be gathered and prepared. And any updates to the process control software should be made and verified. GFP recovery begins with the arrival of the broth tank. A sterile hose is run from the broth tank to the disc-stacked centrifuge, and the tank is pressurized to drive the broth into the centrifuge. After the centrifuge has reached a stable running speed, the inlet valve is opened and broth enters the bowl. The centrifugal force of the rotation forces the denser material, the solids, to the sides of the bowl, much like the spin cycle on your clothes washer, while the liquid flows through and out of the centrifuge. As more broth enters the bowl, it displaces the now clarified, solids removed, liquid to the top of the bowl where it exits, while the cells continue to build up on the bowl surface. The centrifuge has an integrated RPM monitor. If the unit is not rotating at a stable running speed, the controller will alarm and shut it down. The liquid leaving the bowl is known as the clarified stream because almost all the solids have been removed. A sensor monitors the clarified stream for percent solids. When this value rises, it indicates that the bowl is at capacity and the solids must be removed before processing more broth. The solids are the E. coli cells, and they contain the product. When the bowl has reached capacity for solids, the bowl opens and the solids are discharged into an appropriate container for collection. Once the solids are discharged, the centrifugation step can resume, while the clarified liquid is waste. At this point, the cells are in a paste form, and although most of the liquid has been removed, our cell paste is still about 40% liquid by weight. The remaining liquid contains high levels of metabolites and salts that could complicate downstream processing, so we're going to lower those levels by washing the cells. The cell paste is suspended in a buffered solution, and then run through the centrifuge again. As the clarified liquid leaves the centrifuge this time, it carries many of the contaminants from the fermentation step with it. The cells, once again in paste form, are ready for the next step, cell disruption, also called lysing. The cells are resuspended in a buffered solution, and then pumped at high pressure, 900 bar, which is about 13,000 pounds per square inch, through the homogenizer. Inside the homogenizer, they are forced through a tiny orifice. Just like a balloon being tightly squeezed, the cells can't take the stress, and they rupture and break apart. And to ensure that all the E. coli cells are ruptured, the solution is cycled through the homogenizer a second time. After the second homogenization, the lysed cell solution is pumped back through the centrifuge. But this time, our goal is different. Before lysing, our product was held within the E. coli cells. Now, with the cells broken apart, the cell contents, including cytoplasm and green fluorescent protein, are mixed into the buffered solution. The centrifuge again spins out the solids, which are primarily cell debris, and it's the clarified liquid which contains our product, GFP. This time, we discard the solids and keep the liquid, which is now known as lysate. Although the centrifuge has removed almost all of the cell debris, some small particles still remain. We'll remove those with our final recovery process step, filtration. The centrifuge lysate is pumped through a 0.22 micron filter. This filter is fine enough that it removes virtually all of the remaining solid materials. At this point, the process stream is referred to as clarified lysate. The recovery process is finished. The clarified lysate is pumped into a vented, temperature-controlled transfer vessel. This lysate tank then moves downstream to the next series of process steps, purification, where dissolved impurities are removed from the GFP solution and GFP is subsequently concentrated and stabilized.